The research paper discusses new insights into the Lamb shift, focusing on the spectral density of the shift. It begins by highlighting the significance of the Lamb shift in quantum electrodynamics, QED, and its relation to the interaction of a bound electron with the vacuum fluctuations of the electromagnetic field. The authors then delve into different approaches to the computation of the non-relativistic Lamb shift, including those by Bethe, Welton, and Power. They analyze the spectral densities for these approaches, comparing them to those obtained using a group theoretical analysis. The paper emphasizes the importance of understanding the low-frequency behavior of these spectral densities, as it significantly impacts the total energy shift. The authors also discuss the relationship between radiative shifts and vacuum fluctuations, highlighting the role of virtual transitions in inducing the shift. The paper concludes by presenting the results of a calculation of the Lamb shift based on a SO-4-2 group theoretical analysis, which determines the dependence of the shift on frequency without requiring a sum over states. The research paper discusses the Lamb shift, focusing on the spectral density of the shift for the 1s ground state, 2s, and 2p levels. It compares different approaches, including Bethe's, Welton's, and Power's, to the group theoretical spectral density of the non-relativistic Lamb shift. The paper explains how the spectral density provides new insights into understanding the Lamb shift. It details the Bethe formalism, which involves a non-relativistic approach, and how Bethe obtained a finite result by subtracting the divergent term from the total shift. The spectral density in the Bethe formalism is integrated over energy, including a sum over states. The paper also discusses the approximations Bethe made to evaluate the integral, such as assuming the logarithm would vary slowly with m and replacing it with an average value. The final result is an energy shift for s states, which is proportional to the Bethe log. The research highlights the significance of understanding the Lamb shift and its relation to the spectral density for advancing our knowledge in quantum mechanics and atomic physics. In the context of the Lamb shift, a fundamental concept in quantum mechanics, this research paper discusses 3 distinct approaches to calculating the shift in energy levels of atomic hydrogen. The first approach, proposed by Hans Bethe, is based on the idea that the Lamb shift arises from the interaction between the bound electron and the radiation field. This interaction leads to a perturbation in the energy levels, which can be calculated using a non-relativistic approximation. The resulting expression for the shift, given by equation 12, is proportional to the spectral density of the radiation field, which in turn is proportional to the square root of the energy difference between the initial and final states. The second approach, proposed by John A. Wheeler, considers the Lamb shift as a result of the interaction between the bound electron and the quantized radiation field. This method uses the concept of the self-energy of the electron, which is related to the energy shift through the Kramers-Heisenberg dispersion formula. The resulting expression for the shift, given by equation 14, also depends on the spectral density of the radiation field, but it includes an additional term that accounts for the energy of the radiation field. The third approach, suggested by Richard Feynman, is based on the observation that the presence of atoms in a vacuum changes the index of refraction, leading to changes in the frequencies of the vacuum fluctuations. The change in vacuum energy due to these changes in frequency can be calculated using the Kramers-Heisenberg expression for the index of refraction, as shown in equation 19. After subtracting the energy shift for free electrons and converting the sum over frequencies into an integral, the expression for the shift, given by equation 24, is obtained. This expression is similar to Bethe's result, but with a different argument in the logarithmic term, which may become negative at high energies. Finally, the paper discusses a model that predicts the changes in the vacuum field energy as a function of position for each spectral component of the radiative shift, challenging the assumption of a uniform index of refraction in Feynman's approach. This model could potentially provide a more accurate calculation of the Lamb shift by considering the spatial variations in the vacuum field. The authors derive an expression for the energy shift of a level in terms of the generators of the group SO-4-2, which is an integral over frequency. The integrand is the spectral density of the shift, and group theoretical techniques are used to evaluate it. The radiative shift for the 1s level is given by equation 26, where the dimensionless normalized frequency variable phi is defined as equation 27. The group theoretical expression for the Lamb shift is derived from the Klein-Gordon equations of motion using a non-relativistic dipole approximation, assuming infinite proton mass, and minimal coupling with the vacuum field. The level shift is obtained as the difference between the mass renormalization for a spinless meson bound in the desired state and the mass renormalization for a free meson. Second-order perturbation theory is not used. The authors show that the fundamental results from Bethe's spectral density and the group theoretical spectral density are in agreement. The ground state Lamb shift increment E1 can be written as an integral over E equals h omega, which is the energy of the vacuum field in EV. The spectral density of the shift D increment E1, d, is measured in electron volt per electron volt, which is dimensionless. The ground state spectral density from equation 26 is given by equation 29. Figures 1, 2, and 3 show plots of the spectral density of the ground state Lamb shift with Z equals 1 over the entire range of energy E computed from equation 29 using Mathematica. The spectral density is largest at the lowest energies and decreases monotonically by about 4 orders of magnitude as the energy increases to 511 electron volts. The ground state shift is the integral of the spectral density from energy 0 to 511 keV. The log-log plot in Figure 2 reveals that for energy above about 1000 electron volts, the slope is approximately 1, indicating that the spectral density is nearly proportional to 1, e for energy below about 10 electron volts. The spectral density is almost flat, corresponding to a linear decrease as energy increases. The authors will show in later sections that for shifts in S states with principal quantum number n, the asymptotic spectral density for large E is proportional to alpha, Z alpha, 4, 1, and 3, and as the energy E goes to 0, the spectral density increases linearly, reaching a maximum value that is proportional to alpha, Z alpha, 2, 1, and 2. An approximate fit to the ground state data in Figure 1 is given by equation 30. The research discusses the ground state spectral density and its contribution to the total shift in various energy regions. Page 9 presents a linear decrease in spectral density at very low energies and a near-linear change for visible and near-IR energies. Page 10 delves into the spectral density's behavior, showing how the contribution to the total shift changes with energy. The fraction of the total shift from energies below 100 electron volts is about 10%. With energies below 13.6 electron volts contributing 2.5% and those below 1 electron volt contributing 0.25%. The spectral density's shape and behavior are crucial for understanding the energy-dependent contributions to the total shift. Figures and equations are used to illustrate these points, demonstrating the significance of low-energy contributions to the total shift. The discussion also highlights the differences in spectral density between the 1s and 2s states, with the 1s state showing a much larger spectral density at both high and low frequencies. The research emphasizes the importance of considering the spectral density's energy dependence for accurate calculations of the total shift. This research paper presents a comprehensive analysis of the Lamb shift in atomic hydrogen, utilizing group theory to calculate the spectral density for radiative corrections. The paper provides detailed plots and calculations that demonstrate the validity of the group theoretical approach in computing the 1s and 2s shifts, which are essential components of the Lamb shift. Figure 4 illustrates the fraction of the ground state shift due to vacuum field energies between 0 and E, plotted as a function of E on the abscissa. This plot is obtained by integrating the spectral density from the group theory equation, shown in Figure 1. The plot is linear in both the ordinate and abscissa, with the origin corresponding to 0, 0, for all plots. This figure highlights the importance of low-energy contributions to the overall shift, as energies below 30 electron volts account for approximately 0.05 of the total shift. Figure 5 compares the group theoretical spectral density with contributions to the shift in the Bethe formalism for transitions 1s right pointing arrow 2p. 1's right pointing arrow 4p, and 1's right pointing arrow 8p. The complete spectral density, which is the summation of contributions from all transitions, is shown in black. The dashed blue line represents the high-frequency 1, E asymptote. This figure demonstrates the accuracy of the group theoretical approach in capturing the essential features of the spectral density across various energy ranges. Figure 6 showcases the logarithmic plot of the group theoretical spectral density for the 1s and 2s shifts on the vertical axis versus the logarithm of the frequency in EV on the horizontal axis. The dashed orange curve below 1 electron volt is a 2s low-energy approximation derived from group theory or the Bethe formula. The blue curve represents the largest single contribution in the Bethe formalism to the 2s shift for the transition 2s right pointing arrow 3p. For frequencies below about 20 electron volts, the absolute value of the spectral density for the 2p shift increases rapidly in magnitude as the energy is reduced and is much bigger than the spectral density for the 2s shift. The 2s shift cannot have a negative contribution from the lower 1s state since the transition 2s right pointing arrow 1s is forbidden by the conservation of angular momentum. The classic Lamb shift arises from the difference between the two spectral densities, so the negative 2p spectral density actually increases the 2s2p Lamb shift as the energy decreases, figure 8. The total 2p shift is about 0.3% of the 2s shift. Bethe also computed a negative contribution for the shift from the 2p state, 16. Comparing the ground state group theoretical Lamb shift calculations to those of Bethe, Welton, and Feynman, integrating the group theoretical spectral density from near zero energy, 5.4 times 10 to the 7 electron volts, to 511 keV, about the rest mass energy of the electron, gives the 1s shift of 3.4027 times 10 to the 5 electron volts. This result is in agreement with the numerical result of Bethe and Salpeter, who used the Bethe log approximation and obtained a value of 3.392 times 10 to the 5 electron volts, with a discrepancy of about 0.3%, 5. Bethe and Salpeter reported that the ground state Bethe log, which is a logarithmically weighted average value of the excitation of the energy levels contributing to the radiative 1s shift, was 19.77 Ri or 269 electron volts, 16. Due to the weighting, it is not clear how one should interpret this value. The paper discusses the spectral density of the Lamb shift at high frequencies, focusing on the 1s and 2s shifts. It presents a comparative analysis of 4 different methods for calculating the spectral density: Bethe's second-order perturbation theory, Welton's model, Power's calculation based on Feynman's approach, and the group theoretical method. For the 1s shift, the spectral density from all 4 methods converges to a 1e divergence at high frequencies. The Bethe, Welton, and Power models predict identical high-frequency spectral densities, which are proportional to 1, n cubed for s states. In the case of the ground state, n equals 1, z equals 1, the high-frequency spectral density is calculated as 4.488 times 10 to the 6, Ea fit to the last 2 data points near 510 keV in the group theoretical calculations gives a similar result of 4.4008 times 10 to the 6, e. The 2s shift, however, exhibits a 1 e squared divergence at high frequencies, with the spectral density being negative and significantly smaller than the 2s spectral density at 511 keV. Below 20 electron volts, the absolute value of the 2p spectral density is greater than the 2s spectral density. The paper also highlights the importance of the dipole sum rule in evaluating the summation for the spectral density. It emphasizes the role of vacuum fluctuations in the Lamb shift, as demonstrated by Welton's model, and the necessity of providing a low energy limit for integration to obtain a level shift. The choice of the lower limit as the Bethe's log average excitation energy and the upper limit as mc squared ensures that the total 1s shift agrees with Bethe's calculation. Overall, the paper provides a comprehensive comparison of different approaches to calculating the spectral density of the Lamb shift, shedding light on their strengths and limitations, particularly at high frequencies. The authors present a comprehensive analysis of the spectral density of the Lamb shift at low frequencies. Figure 9 compares the group theoretical calculated spectral density with the theoretical high-energy 1e function, demonstrating a remarkable agreement within 2% at 511 keV and 6% at 50 keV. The asymptotic theoretical result is a reasonable approximation down to 50 keV. The authors derive the low frequency limit of the spectral density of the Lamb shift from the Bethe spectral density, expanding it to first order in E. The resulting equation, EQ 42, is evaluated using the sum rule and the Thomas Reich-Kuhn sum rule, yielding EQ 45. The corresponding spectral density for n equals 1, Z equals 1 is given by EQ 46. As E decreases to 0, the spectral density increases linearly to a constant value, which is independent of n. The group theoretical result is analytically derived, yielding exactly the same result as the Bethe formulation, EQ 47. Figure 3 shows the results of group theoretical calculations of the spectral density of the ground state Lamb shift, demonstrating a near linear increase in the spectral density as the frequency decreases. The authors also explore Power's approach at low frequency, deriving EQ 48, which is identical to the second term in the low E approximation to the Bethe result. This leads to EQ 49, which is identical to the frequency-dependent term in EQ 47. The theory of Feynman proposes that the vacuum energy density in a large box containing H atoms increases uniformly with the addition of atoms. To develop a model of the spatial dependence of the change in energy density, the authors relate the vacuum field and the radiative shift. The spectral energy density of the vacuum field with no H atoms present is given by EQ 50, which is converted to EQ 51 to measure frequency in EV. The question being addressed is, what volume of vacuum energy of density ρ0, E, is required to supply the amount of energy corresponding to the Lamb shift? Here is a combined summary of pages 17 and 18 of the research paper. The authors investigate the radiative shift in the context of quantum electrodynamics, specifically the Lamb shift. They introduce the concept of a spectral shift density, which is a function of frequency omega or energy E of the vacuum field. The integral of the spectral density from E equals 0 to the rest mass energy of an electron gives the radiative shift. The authors report on calculations of the spectral density of the level shifts for 1s, 2s, and 2p states based on a group theoretical analysis and compare the results to the spectral densities implicit in previous calculations of the Lamb shift. The total radiative shift increment E1 is expressed as the integral of the vacuum energy density ρ0, E, over an effective volume 5(1), E. By comparing this equation with the definition of the spectral shift, the authors determine that the effective spectral volume 5(1), E, contains the amount of vacuum energy at energy value E that corresponds to the ground state spectral density at the same energy E. Figure 10 plots the log of the spectral volume 5(1), E, versus the log of the energy E, showing that for energies above about 100 electron volts, the spectral volume is less than 1 cubic angstrom, approximately the volume of the ground state wavefunction. The authors calculate the spectral density of the level shifts for 1s, 2s, and 2p states using a group theoretical analysis and compare the results to previous calculations. They find that the group theory approach, as well as the approaches of Bethe, Power, and Welton, all show the same 1e high-frequency behavior for S states above about E equals 1000 electron volts. The calculations also reveal that low energies contribute much more to the shift for a given spectral interval than high energies. Energies below 13.6 electron volts contribute about 2.5%, while half the contribution to the 1s shift is from energies above 9050 electron volts. The 2p shift has a very different spectral density from an S state, being negative and having an asymptotic behavior that goes as 1e2 rather than as 1e. The authors also discuss the eigenstates of a charged non-relativistic particle in a Coulomb potential, which are obtained by solving Schrödinger's equation. The summary begins by describing the equation for the hydrogen atom, specifically the equation for the eigenstates of 1z alpha. It highlights the kernel K1, A, as bounded and Hermitian, ensuring the eigenstates form a complete orthonormal basis. The dilation operator d, lambda, is introduced, allowing for the transformation between the usual energy eigenstates and the eigenstates of 1z alpha. The relationship between these states is demonstrated, showing that the usual Schrödinger energy eigenstates can be expressed in terms of the eigenstates of 1z alpha. This connection is crucial for momentum space calculations. The summary then moves on to the group theoretical approach, focusing on the derivation of the shift spectral density. It explains how the group theoretical approach avoids the need for a complete set of states, unlike Bethe's result. The real part of the shift is calculated, involving the matrix element omega NL. This is contrasted with the new basis states, NLM. A, which are eigenstates of Z alpha -1 and complete with no scattering states. The generators of SO, 4, 2, are introduced, including gamma 0, gamma 4, and S, which are used to define the algebra of SO, 4, 2, generators. The commutators of these generators are also discussed, highlighting the closure of the algebra. The research paper presents a novel approach to calculating the level shift of a hydrogen atom in a magnetic field, utilizing the SO, 4, 2, symmetry group. The authors define a three-vector of generators, gamma I, proportional to the momentum, and derive an expression for the level shift, increment NL, as a function of the magnetic field strength, alpha, and the principal quantum number, n. This expression is given by equation B17, which involves an integral over the variable s and a function mnLs that depends on the eigenstate, nl. To simplify the calculation of mnL, the authors introduce a generating function for the shifts for any eigenstate characterized by n and l. They multiply equation B17 by n⁻4 e⁻, beta n, and sum over all n greater than equals l plus 1. This leads to equation B21, where the right side is expressed as a sum of exponential terms in the variable psi. By applying a J transformation generated by e⁻, I phi s, the authors transform the trace to find a simpler expression for the sum, given in equation B21. The paper then proceeds to find a particular MNL by expanding the right side of equation B21 in powers of psi and comparing it with the left side. Using the multinomial theorem, the right side of equation B27 becomes a sum of exponential terms in beta, as shown in equation B28. This result allows for the calculation of the level shift for any eigenstate, NL, in a hydrogen atom under a magnetic field. Here is the combined summary of pages 23 and 24. The expression for MNL is derived as a summation over R, S, T, and other indices, where R plus S plus T plus equals N and R plus S plus T plus greater than L. This expression is used to calculate the radiative shift for the 1s ground state and the 2s2p level. The radiative shift for the 1s ground state is given by equation B30, which involves an integral over the variable phi, and the shift for the 2s2p level is given by equation B31, which involves a similar integral. These expressions are used to calculate the Lamb shift, which is a fundamental concept in quantum mechanics. The references provided include classic papers by Lamb and Rutherford, Bethe, and Welton, as well as more recent works by Maclay and others. The Lamb shift is a result of the fluctuations of the electromagnetic field in the quantum vacuum, and it has been the subject of extensive research in the field of quantum electrodynamics. The paper also acknowledges the contributions of several researchers, including Professor Peter Milani and Professor Lowell S. Brown, who provided valuable insights and discussions on the topic. The paper is a culmination of the author's research in this area, and it provides a comprehensive treatment of the Lamb shift and its significance in quantum mechanics. Finally, the paper notes that there are 2 typographical errors in the manuscript, which are corrected in the errata. The paper also provides a list of references, which includes a range of classic and modern works on the topic of quantum electrodynamics and the Lamb shift.